the amplification, and it's going to be by Kunal Talwar.
Thanks. So this is joint work with Ali Feldman and Elia Marinov from Google and Abhiradeep Thakurta, who is at UC Santa Cruz and is a visitor at Google. Okay, so this work deals with differential privacy. So let me start out with defining or reminding you what differential privacy is. So differential privacy is a definition for a randomized algorithm. It's a property that an algorithm satisfies or may not satisfy, so we'll be thinking of algorithms that sit between some data set, let's say x in d to the n, and a curator or an analyst that's trying to learn something about the data set. Let's imagine two universes. The red universe, the blue universe here, where one of the rows in this data set is my data, right here. And the red universe where I've gone in and erased my data from the data set. Differential privacy stipulates that this curator, which will be a randomized algorithm, has the property that the analyst sitting on the other side cannot tell which universe they are in. So the distribution of the mechanism's outputs, m of x and m of y, on neighboring data sets x and y, are essentially indistinguishable. To be a bit more precise, we'll require this indistinguishability in a multiplicative sense. So let me define that more precisely. We'll be using a definition of a version of differential privacy that you may not have seen before. This is what we call Renyi differential privacy. So differential privacy says that this ratio, the probability that the mechanism on x outputs some value z, divided by the probability that the mechanism on y outputs some variable z. Differential privacy requires this variable to be not too large. And we'll measure this largeness in terms of the expectation of the alphath power of this random variable, when the z itself is drawn from the distribution y. And we take logs and normalize just to kind of make it compatible with the usual definition of differential privacy. This complicated expression is not something we came up with. This is what's known as the Renyi divergence between two distributions. This is a very well-studied notion of divergence between distributions that has been studied in information theory. And we'll say that a mechanism satisfies alpha epsilon Renyi differential privacy if the order alpha divergence is bounded by epsilon. Now you may ask, why am I using this definition? I guess the only real reason is that the math for this paper becomes simpler with this definition. This is essentially equivalent to the more common definitions that you may have seen. So from this, you can easily go to epsilon delta differential privacy. In most settings, in fact, this definition is actually nicer in that for many algorithms, the best analyses that you get for epsilon delta privacy of those algorithms goes via this definition, both theoretically as well as practically. So, and I guess as we'll see in this paper, in this talk, this definition actually is very nice to work with. Good. Okay, so I guess this is a complicated expression. I don't expect you to try to parse it right here. The only property of this notion of divergence between distributions that we'll be using in this talk today is the following. If I take a Gaussian centered at 0 and another Gaussian centered at 1, the order alpha divergence between those two Gaussians is equal to alpha divided by twice the variance of the Gaussian. Right? So one of the very commonly used mechanisms in differential privacy is what's known as the Gaussian mechanism for, say, releasing the sum of a bunch of vectors. The Gaussian mechanism takes the sum and adds some Gaussian noise to it. Surprise, surprise. And I guess this statement is essentially equivalent to saying that this Gaussian mechanism satisfies alpha over 2 sigma squared Renyi differential privacy. Okay, so let me start with the motivating teaser problem. Now that I've set up differential privacy, let's think of this problem. So this is the population risk minimization problem. You are given a population of functions f, w, x, where and your goal is to minimize the expectation of this function when x is drawn from some population, some distribution. We'll be assuming that this function f is convex, smooth. Just by scaling, we'll assume that the gradients are bounded by 1, and the diameter of the constraint set is 1. So these are just normalization assumptions. This is a ubiquitous problem in machine learning. Pretty much all of modern linear machine learning falls in this framework. So how well can we solve this problem? If I gave you t samples from this distribution, without privacy constraint, you can get an optimizer or an approximate optimizer, which gets error in this estimation of roughly about 1 over square root of t. And if you want to do this with differential privacy, the best known bounds have a square root d dependence on them. And moreover, we know that this is unavoidable. So this is a very commonly used setting where we know provably that differential privacy incurs a large cost in utility. And one of the questions we'll be hoping to answer today is, can you get around this lower bound somehow? Okay, so let's go back to this question and ask, how does one solve this problem? So if one didn't worry about privacy, one of the algorithms that solves this population risk minimization problem is the following very simple and very well-known algorithm called stochastic gradient descent. You have your t samples from the distribution, x1 through xt. You start at an arbitrary w naught, and then in every step of the algorithm, you look at the gradient of the loss function at the next data point, and move a small amount in the direction opposite to the gradient. You do this for t steps, and then you output your final answer. This algorithm gives you the 1 over square root t rate. This, of course, is not private, but notice that the only place where this algorithm actually uses the private data, x1 through xt, is in computing the gradient here. This gradient is a d-dimensional vector, which we assumed had norm at most 1. So this is something we know how to make private. So this gives me a noisy stochastic gradient algorithm, where I just add some Gaussian noise to this gradient. Right? And now we can analyze this algorithm. Let's try to see how to analyze this. We saw that the Gaussian mechanism gives me alpha over 2 sigma squared Rényi differential privacy. This algorithm runs for t steps. So differential privacy enjoys this really nice property called composition, which allows me to figure out how my privacy cost accumulates over time. Since there are t steps, it actually just accumulates linearly, and you get something like alpha t over 2 sigma squared. This is a really large privacy cost. If this is what we were getting, we would not be very happy. We know other algorithms for this problem that do much better. Fortunately, there are tools that allow you to give a much better analysis of this algorithm. And that tool is what's known as privacy amplification by sampling. So there's this really very nice theorem of Kasi Vishwanathan et al., which says the following. Suppose you have a alpha epsilon RDP algorithm, say the Gaussian mechanism. And now instead of running this mechanism on your whole data set, you choose a random q fraction of your data set and run your mechanism on that sub-data set. This theorem says that this new mechanism has vastly improved privacy properties. My epsilon suddenly became q squared times epsilon. Note that q is much smaller, q is smaller than 1, so this is much, much smaller privacy cost. Right? And with this dramatic improvement in privacy cost, we can reanalyze the algorithm or a slight variant of that algorithm. Instead of using the tth data point in the tth step, let me pick a random, uniformly random data point from all the t data points in each step and use the gradient of that data point. This mechanism originally, without this, had alpha over 2 sigma squared RDP, but this data point xj is a random 1 over t fraction of my data set. I get a q squared boost, so my privacy goes down to alpha over 2 t squared sigma squared. Right? And now, again, since I actually do this for t steps, I pay a factor of t, but now my privacy cost is actually going down with t. Right? This is a really nice result. This technique has broad implications to all of differentially private machine learning, not just to the stochastic gradient descent algorithm, but to other algorithms in machine learning like EM, like variational inference, stochastic gradient Langevin dynamics, and so on. So this is nice. Can we go home? Right? So I guess I want to point out some deficiencies of this really nice privacy amplification by sampling argument, which motivate the current work. Right? So there's I guess 2 main deficiencies. First, this privacy amplification by sampling applies if I keep the sample hidden. So recall that I picked this j at time step t uniformly at random. If I told you what j was, this is false. The reason I actually got this large privacy boost is that the analyst does not actually know what j is. And hiding this sample actually gives me more privacy. But there are settings where this is an unreasonable requirement. So if I'm trying to run a machine learning algorithm in a more distributed setting where these data points are clients communicating with me, it's unreasonable to assume that no one can observe who is communicating in what round. In many settings, I can't control the order in which these clients come to me, so I can't assume that it's random. Right? So this need to hide the random samples is a serious restriction in many settings. The other deficiency is that I lied to you. I told you that this privacy improves to q squared times epsilon. That's not quite true. It improves to q squared times epsilon times some factor which grows as e to the epsilon. So if I start out with an epsilon which is small, say at most 1, then this is great. 1 plus e to the epsilon is like a small constant factor. And I'm getting a large q squared boost. I can afford to do that. But I can't hope to do this if my sigma was much larger than 1, or if my starting epsilon was much smaller than 1. Sorry, the other way around. If my sigma was much smaller than 1, then the starting epsilon is much larger than 1, and then e to the epsilon is a very large penalty to pay. And this is not just an artifact of the analysis. This algorithm is actually not very private if I don't add a lot of noise. The other motivation for this work is that if we go back to the analysis, we use this composition theorem, and essentially what that's saying is that you're allowed to publish the whole path of your SGD. So I started with some point W0. I can publish W1, W2, all the way up to WT. Even though I only care about outputting WT, which is the final iterate, I'm in some sense paying the cost of outputting all of them. Right? And in some sense, philosophically, that's a little bothering in that the fact that I don't need to output all the other WIs doesn't actually buy me any more privacy, whereas intuitively you would think that it should. So these are the deficiencies that we address in this work. We give a new privacy amplification theorem, which does not need the secrecy of the sample. It does not need the samples to be random samples. It could be a fixed known order. Instead, I'll assume that the iterates themselves are secret. So if you only publish WT, we'll argue about how private that is. The analysis that we have only doesn't apply to, is not as general as privacy amplification by sampling, but applies to a reasonably large class of algorithms, which I'll define next. Okay, so let's recall the definition of a contractive map. A function psi mapping d-dimensional vectors to d-dimensional vectors is called contractive if it doesn't increase distances. So if I have 2 points x and y, their distance after applying the map is no larger than what it was before applying the map. And this is the Euclidean distance. So we'll define this class of algorithms called contractive noisy iterations. So the sequence is defined by a starting point x0, a sequence of contractive maps psi1 through psi t, and some noise scale sigma. And it's the process that you would expect. At each step of this process, I take the previous iterate, xt, apply this contractive map to it, and then add some noise. I repeat this for t steps, and I output the final xt. Right? I'll call that CNI sub t with these parameters. And the reason we find this class of algorithms interesting is that, in particular, if you do gradient descent with convex and smooth functions, they are in fact contractive. These gradient descent steps are actually contractive. Also, projections to a convex set are contractive. So projected gradient descent, as we defined, falls into this family. Okay, and we would like to say that these kinds of algorithms enjoy a very strong privacy guarantee. So let's think about, to get some intuition, let's think of a very special case when these maps psi sub t are all equal to the identity map. In this case, it's very easy to understand what this process is doing, and I think you can all see that this process after t steps simply adds noise of variance t times sigma squared to the initial point. What that means is that if I consider two starting points, x0 and x0 prime, whose distance is at most 1, then xt and xt prime are samples from Gaussians with means 0 and 1 and variance t sigma squared. And therefore, the order alpha divergence between xt and xt prime is something like this. Of course, in general, for arbitrary contractive maps, the noise may disappear when I apply the contractive map. And so it's not the case that the final xt actually has a variance as large as t sigma squared. And what we show is that even though that may happen, the identity is indeed the worst case. So if you have an arbitrary sequence of contractive maps, you still have exactly the same bound of alpha over 2t sigma squared on the divergence. So intuitively, if your contractive map destroys some of the noise, it also destroys some of the signal. And that's what this analysis kind of takes advantage of. Okay, so let me say a few words about how we prove such a theorem. Note that the starting assumption is a metric assumption. It's saying that 2 points are at Euclidean distance at most 1. The conclusion that we want to get to is an information theoretic conclusion, which knows nothing about any metric structure on the Euclideans, on R to the D. Right? And this is some kind of a mismatch. If we think of a proof as a negotiation between the assumptions and the conclusions, these two don't speak the same language. This thinks of R to the D as a metric space. This doesn't know about any metric structure on this space. So what we do is we give them a common language. So towards that goal, let me remind you of the definition of Wasserstein distance. we'll be using the L infinity Wasserstein distance, which is simply the infimum of the longest edge in a matching, overall matchings between the two distributions. So if I have the yellow distribution and the green distribution, and I match them up in the natural way, the L infinity Wasserstein distance is the length of the longest edge. And in the more general case, you define it using couplings. The new definition that gives them a common language is what we call a shifted Rényi divergence. So the shifted Rényi divergence between two distributions, P and Q, is defined as, I look at a Wasserstein infinity ball of radius z, z is this parameter here, around P, and I look at the divergence between P prime and Q, and I take the min over all possible P prime in this ball. Right? If I'm trying to minimize this alpha divergence over all points in this L infinity ball, that's the shifted Rényi divergence. And now I have a common language. If you think about it, the starting assumption says that the one shifted Rényi divergence between x0 and x0 prime is 0, because I can shift x0 to x0 prime by moving a distance of 1. The desired conclusion says that the 0 shifted divergence is bounded. So at least they are talking the same language. Now I need to find a way to reduce this 1 down to a 0. And that is achieved by the following lemma that we call the shift reduction lemma. It says that if you have some shifted divergence between P and Q, and you add some Gaussian noise to P and Q, the shifted divergence, I can reduce the shift by a small amount and pay for it in the divergence. So I can, when I go from P to P twiddle, where P twiddle is P plus noise, Q twiddle is Q plus noise, I can reduce the radius of this ball by a small amount, and the length of this blue thing increases by an amount that I can control. Once I have this lemma, proving the theorem is not very hard. The starting assumption talks about the one shifted divergence being 0. I do one step where I reduce the variance a little bit, and I pay for it in this, reduce the Wasserstein distance a little bit, and I pay for it in the divergence. In the next step, I reduce the radius further, and in t steps, I ensure that the radius goes to 0, and I'm just left with a bound on this alpha divergence. The rest is pretty much arithmetic. In particular, this does give me a way to analyze the noisy SGD algorithm, even in the case when the ordering is not random and hidden, but known in public. And you get essentially the same bounds as you would get from privacy amplification by sampling, which are tight. It also allows us to answer the question that I started with. So we know that for this problem, there's unavoidable d-dependence in how much error I need. A result can be used to show that if you give me a small amount of public data, so say a small number of people opt in, with roughly d public samples, I can get error which is the same as the statistical error, which is the best I can do without privacy constraint. So this overhead of requiring differential privacy goes away if I have a very small amount of public data. So to summarize, I told you a bit about privacy amplification by sampling. I told you why that's often inadequate. And we saw a new privacy amplification theorem that I think is the first theorem of this kind where you gain privacy by hiding intermediate steps of the algorithm. And hopefully we'll have more. In terms of applications, it recovers results analogous to privacy amplification by sampling, even if the order is not hidden, and it gives you some new results in the public-private setting. I'll stop here.
Unfortunately, we don't have time for questions, so let's take them offline. And, let's thank Kunal again.